because there were some slides that we didn't get to last time that I wanted to talk about a technique called singular value decomposition. So singular value decomposition indeed is a matrix factorization method, okay? And it claims that it is a magic method that given a matrix M, okay, will factor it into the product of three matrices. If this is a, let's say, a, okay, it will factor into three matrices, okay, U, D, and V, with the property that the middle one, D, is only going to be a diagonal matrix, okay, meaning that the values are only going to lie on the main diagonal. And there's some other definitions of diagonal when the thing isn't square. But does everybody see everything else is 0 except this main thing? So what is interesting about it? If you have a diagonal matrix and you multiply it by a matrix, this is basically weighing the elements of each column. That is what multiplying, if I make this thing 100 and I multiply a matrix by it, that entire column, the first column, will all get multiplied by 100. Does everybody agree with that? Okay. So what is interesting about this factorization is that it does give us a way to decompose it. It doesn't make it, unfortunately, nice and sparse here, because it looks like if this was an n by n matrix, this would be an n by n matrix times an n by n matrix times an n by n matrix. But what's the point? The column D is going to, the numbers, the values of those weights are going to measure in some sense how important that product is, that column is, okay, of the corresponding matrix. And so what we can do now is, if we do a singular value decomposition of the matrix, we can drop, okay, in some sense, the rows and columns of this that will correspond to less important features, and that will give us a good approximation of the matrix. Any questions about that? So what does that mean? What?
N equals to, right?
Yes.
It is not an approximation, right?
This should not be an approximation, but it isn't magical. If you want to take a look at it, this is now an n by n matrix. I am now expressing an n by n matrix by the product of three n by n matrices. So this by itself is not magic, right? But what is kind of good about it is one of these things naturally corresponds to weights of importance, and the others basically define kind of matrix products that are going to help us here. So what happens if we multiply a, let's just think about it. If we have an n by 1 matrix and an n by 1 matrix and an m by 1 matrix, we multiply them, what do we get? An n by m matrix. Does everybody see that? So one of these rows, in some sense, and one of these columns multiplied by itself gives us an n by m matrix, right? In fact, one can, this is basically voodoo for saying that the way that you can express matrix products as basically sort of the sums of these, matrix products for each, appropriately summed over the appropriate pairs of vectors. So if I think about it, if here I've got k levels and k levels, okay, let's take it back. If I want to multiply an n by, x by m matrix, okay, I can express the product of these as being the sum of these matrices for x of these, the xth row against the xth column. Okay? That's what this is magically saying. And the result is that each row and column, as we move along this matrix, will give us a matrix of the desired size of the product, where this D value tells you which is most important. So what is the point there? The point is that if we take the this matrix product, okay, let's remember, go back to his thing. We can view the matrix, the SVD of this thing, as being constructing a matrix U and a matrix V, okay, such that because it's being multiplied in between by this diagonal thing, okay, we're only going to be multiplying the ith column of U against the ith row of V, okay? And the value of that is governed by the corresponding parameter for D. So it means that we are expressing M as the sum of X different products, and we know the weight of these products, because that's what that diagonal matrix tells us, the value of D does. So we can do something like this. We could identify, using the values of D, which are the most important rows and columns of this thing, and represent the entire matrix by just using the most important rows and columns. This is our U, this is our V, okay? And we're looking for what are the most important ones. And if we had all rows and all columns, together we would multiply that and get the full matrix. But if we drop the ones with smallest d, we get an approximation. And the claim here, this is kind of a graph showing you, this is a measure of error. This is a measure of how many of these singular rows and columns you include. And in general, with these things, the amount of error you get decreases rapidly. So a relatively small number of rows and columns suffice to explain the entire matrix. Does everybody get that idea? I find it easier to look at this from a picture. Yes? What?
So this is the error between the matrix that we construct by taking one row and one column of the two matrices against the total product.
Right. So what we're going to be doing is thinking about what we're doing. Each one of these, as we add another row and column to our SVD, if we include, let's say we only include the most important row and column. That row and that column will give us a matrix of the right dimension. That is an approximation of the image, of the matrix. If we now take the second most important vector and multiply it by the second most important, row vector, we will get an image, a matrix. And if we add that to this, it will be a better approximation. If we added all of these things together, it would be such a good approximation, it would be perfect. But if we drop the ones with the lowest multiplier value, D, they will have less effect on the big matrix. Does everybody get that idea? And so this is the kind of thing that happens. What is this? Does anybody recognize who this guy is? Forget this guy. Who's this guy? Does anyone know? Can you recognize him from where you are? It is Lincoln, okay, I guess. But the impressive thing, this is a 512 by 512 image of Lincoln, built by just the first 5 of the singular vectors here. If we think about it, it was a 512 by 512 image, right? Keeping just 5 of the vectors, since we're keeping 2 of them on this side, 5 on this side, and 5 on this side. This is about 2% of the numbers of the original matrix. Does everybody see that? It's equivalent to about 2% of the features of the original matrix, and it does a very good job of roughly approximating what's going on. Does everybody see that?
How would we know which 5 have the most information? There could be any.
How do you know which ones have the most information? If you look at the factorization, this middle product D is a diagonal matrix, which means that it's got all values, anything that's non-zero is lying on the main diagonal. And some of the numbers are bigger than some other of the numbers, right? The bigger ones, when we are going to, the whole thing is going to be basically the product of the row times the product of the column times this number. this number governs how important that row and column are. So simply selecting the the rows and columns corresponding to the biggest numbers gives us an approximation of the matrix. Okay, relatively simple. That where a small number of these vectors will explain a large part of the matrix. Yeah.
So using SVD, we are doing dimensional scaling and as well as scaling the number of rows down to the most important.
We're doing what I would say is dimension reduction. That's the important thing that I'm thinking. Because I want to say that if I was specifying, sorry about that, here in this Lincoln image, this would be 512 by 512. That would be 512 rows, 512 columns. That's a 500, and, think of that as a 512 dimensional thing. Okay? Now what we would like to do is to reduce this. Okay? If we can build an approximation of this, instead of using 512 features in some sense, we now use 10 features or 20 features or 30 features, we're better off. That much should be clear.
And are we scaling the number of rows as well? Scaling down the number of rows as well?
Rows and columns. The approximation that we're getting is this. This is the approximation of the matrix. Remember, originally it would be a 512 by 512 matrix, right? If we're keeping 50 singular values, there's 50 values for the, from the U matrix, and 50 values from the V matrix. Okay? Originally, we needed a 512 by 512 elements to express the image, right? Now here, we're needing 512 times 100. So we've reduced the number of features by 1/5. Okay? And if you look at this one, anybody who knows Lincoln is not going to have a problem picking this guy out, right? This is a very, very good approximation to what you would get. This is the difference between the right picture and the wrong picture. But so yes, there are little bits of error. But it should be clear that here we've reduced the amount of data that we need to represent this matrix. And likewise, if you can now reduce what was a 512 by 500, let's say you had 512 features here, okay? If we can reduce it to 100 features that capture basically all the information, this is a better thing. Does everybody get that idea? And in fact, what this kind of shows, this is only 10, would be the equivalent of 10 features, okay? And it should be clear that even this approximates a lot of the structure of what's going on, right? So what SVD is an important thing. It's a way that you can take a complicated space of features and boil them down to a smaller number of features with the property that anything you could recognize with the other ones, okay, you should be able to recognize with these. Any questions? Okay, yeah.
The size of the new image will still be 512 cross 712, right?
The size of the reconstructed matrix is still going to be 512 by 512, right? This is the reconstructed matrix. In general, if you have an n by m matrix, we are certainly going to get an n by m matrix even if we use only one vector. The trouble is it's going to be very blocky. It's not going to be very... But as you add more and more, you fill in more and more detail. And it gets better and better. So if you have a problem where you've got a huge number of variables, if you build that matrix and you do an SVD on it, okay, you will now be able to identify a small number of features that will explain all the features you had, okay? And building a model from these compressed features is probably more robust and simpler and requires less training examples and all this kind of stuff, okay, for the other ones. Any questions? Okay? So this is a good thing, and so you should be aware of a singular value decomposition. Any questions? Okay? What?
I feel like my problem goes deeper than this lecture.
Okay, yeah. What?
I just didn't understand the concept of SVD.
Okay, let's first, what does it do? There's a question of how does it do it is a separate question. But what would be great is if I had a matrix that was n items by m features. And I could tell you that you could build a matrix that was n rows by, by k much less than m features, such that any model you did to predict things about the items here would be almost as good as the ones built on here. You're better off. Does everybody kind of see that? You could imagine having a feature matrix where it's writing down all kinds of features about people in this room, okay? And we'd have their height, their weight in grams, their weight in meters, their weight in lots of other things, okay? How much they weigh without their clothes, how much they weigh with their clothes, okay? You could imagine a lot of different properties here. And if you wanted to then predict something about them, what did you want to predict them? Their high school, their IQ, the major they're going to have in college, something like that. The claim would be that this boiled down feature matrix with only k dimensions is going to encode almost all the information that was there. And because now you're fitting it with a smaller number of parameters, you can probably build a better model on this than on this, okay? And that is why SVD is a good thing. When you have a large number of redundant and useless features, okay, these things can get compressed, okay, in this way, in a rigorous manner. Any questions? Okay? Any questions? Okay. So what I'd now like to talk about is the linear algebra way of building models, or a common technique called linear regression, okay? Which is, I will say the, simplest and, probably in some way most popular modeling method when you've got numerical feature values and you want to predict something, okay? Linear regression basically asks the problem that I am given n points in a certain dimensional space. Here, the dimension is 1. And I want to find the best line that goes through those points, okay? It fits those points, okay? So again, if y is the dependent variable, my target that I'm trying to predict, and x is the input variable, the good thing about this regression line is for any value of x, it gives me a way to predict what the corresponding value of y will be, right? That's why linear regression gives us a model, okay? It lets us make predictions. Now for any value of x, somebody comes along at 53 pounds. No one has ever done that before. Now we can predict how smart they are, or whatever else what the y is. Any questions? Okay? So linear regression is a good thing, okay? Although it does depend upon linear functions. Now, why is it that we like to think about linear relationships? A linear relationship between a variable c and a variable y, x and a variable y, means that there's some constant times x that's equal to y. Okay? Now, why do we use linear relationships? Well, first of all, they're easier to work with. Okay, the theory of linear regression works because of its linear functions. Okay, but for many things, linear relationships are appropriate to at least some degree. So let's look at these and see how appropriate we think they are. Do we believe that income grows linearly with the amount of time that you work? You say no. Who here says yes? You say yes. Why is it yes? If you are paid at an hourly rate, then yes, income grows linearly with what you're being paid. If we had Bill Gates's salary in terms of dollars per hour, if he makes $23 million per hour, then yes, we have that, right? That if Bill Gates stopped working, I imagine he would have less money, right? If he immediately. But again, it's certainly true that in an hourly sense, if you are paid an hourly rate, income grows with time worked, right? You're questioning whether the amount that you make per hour work grows with how much you work, okay? And that maybe is less clear, right? But so there is somewhat of a linear relationship here. Do we believe that housing prices grow linearly with area, the area of the house? People seem to believe that. What would that mean? That would mean that if I give you twice as big a house, you would pay twice as much for it. People think that's right? Given the location's the same, you know, maybe. I mean, do I believe that? Maybe that's how the world should work. My guess is that, you know, if I have a choice of living on the street or living in a, a studio apartment, okay, the studio apartment is infinitely better than living on the street, right? But now when you say is it twice, is giving me an extra bedroom twice as much, I don't know. Well, but presumably cost has something to do with it. But basically, again, I think that we believe here to some extent housing prices probably grow something like linear, okay, with that. Does weight increase linearly with the amount of food it is eaten? Do we believe this? Okay. It should be clear that weight increases with food eaten. Do we believe it's linear? That somebody who weighs 300 pounds eats twice as much as someone who weighs 125 pounds? I don't know that that's true, okay? But when you're building a linear regression model, this is kind of what you're assuming. Does that kind of make sense? And are these things right? Not necessarily. Is it a terrible thing to build a model this way? Probably not, but we should recognize that the world is not necessarily linear. So one rule I learned about that someone said that if you want a function to be linear, the key is only to measure it at 2 points. Does everybody see that? But in general, things are not always going to be linear, and that's something that's going to be a limitation of linear regression, which we can work around to some extent, okay, but not as much as some other methods. Any questions? Okay, good. Now, how would we find the best fitting line for a point? Okay, line going through points. And what I want to convince you of there's kind of two properties of this that may seem magical. Okay, what do I think by magical? You guys should know and believe about linear system solving, Gaussian elimination and things like that. You've solved systems of equations. What is solving a system of equations? Okay? It really is saying, when you're solving a system of equations, what you're really saying is you have a bunch of lines, okay, and you're trying to find the point that goes through all those lines. Does everybody kind of believe that? Now, what are we trying to do with linear regression? In principle, we'd like to say these points lie on a line, and we're trying to find the line that goes through these points. Does everybody see that it said that way? It seems like a similar problem. Okay? So there's two differences here between linear system solving and linear regression. First, we reverse roles and points and lines. And second, the word all has quotes on it. In solving a linear system, we want the, the single point that really lies on these lines. In linear regression, the line isn't presumed to go through all the points, right? We want the closest line to it. So there's the issue of points to line swap and, and the notion of all, okay? Now, the points to line issue is not really a big deal. There's this thing called a duality transform, where you can show that if you have a space where if you have points in one space, any point ST can and S and T are is two parameters. That's a point in 2 dimensions, right? A line y equals Sx minus t is a line where the parameters are 2 dimensions, right? S and t. So a duality transform is a way of converting points in one space to lines in another space. And there are magical properties of these things. And so that transform I showed you had the property that if we took this drawing, which consists of a total of 5 points and 3 lines and 2 lines, this goes to what should be 5 lines and 2 points. Does everybody see it? And the red thing is a point that lies on both lines. This red line is a line that goes through both points. Does everybody see that? So there's a magical, again, you have to work out the geometry and see what this is like, but magically through this duality transform, what looked like points in this side look like lines here. What looked like lines on this side look like points here. So if you want to find the line that goes through all the points, what do? You can convert it back to points and to lines and then find the point that lied on all the lines, and that's just linear system solving. Any questions about it? Okay? So that aspect of regression shouldn't seem weird. What should seem a little bit more challenging is the fact that we are trying to, instead of, any questions about the duality thing?
Yeah,
Why? Well, okay, first of all, let's just first see how. There's questions of how and why, okay? How? Do you see what I am doing to convert a point to a line? I'm interpreting whatever a point ST. If you tell me this is a point in line space, that is going to be the line y equals sx minus t. Okay? If you have a line, how do I interpret it as a point? That's going to be the slope, comma, minus the intercept, right? So it should be clear that if you give me a set of points and lines in one space, I can redraw them in this other way, right? That much should be clear. Why does this magic property of adjacencies being preserved work? Well, that's why this transformation was chosen, because they do work that way. And why? That's why you need a proof, okay? But it does have the property that this transformation has the property that it does what we want. And that a lot of useful things in geometry fall from that. Okay? Any questions? Okay, good. So now let's think about error. And what we would like to do is, how do we measure the error in a linear regression fit? Okay? Now, if we think about it, here we've got a variable x. Here we've got a line that goes through. Here's the value we're trying to predict, that's y. We have a line that fits it. How would we measure the error from this? Okay? The residuals that are used when people calculate least squares fitting is they take the difference between f of y, okay, and and between the actual y value and f of x. Does everybody see that? So really what we're doing is we're not measuring the distance between a point and the line, which might very well go at a, will be tilted, okay? Instead, we are measuring it sort of orthogonal to the x-axis. That's kind of an important point here, right? And so that's what it is. The difference between the y value and our predicted value is the residual error, okay? And the standard least squared curves fitting algorithm has the property that it finds the line that minimizes the sum of the squares of these residuals over all points. Okay? Any questions?
Why are we measuring this vertical, not the perpendicular?
Why are we measuring it? Well, first of all, it actually is the right thing. Because if you think about it, what you care about is how different is your prediction from the real thing. Right? Does everybody agree that, if x was weight and y was height, okay? the y value of this point is the actual height for this guy's given his weight, right? And the f of y, f of x is exactly what our prediction is, right? So the difference between prediction and actual is exactly what we are doing here. So it's actually the right thing to be doing if we want to measure our accuracy as a predictor. Any questions? Okay. Now, why do they minimize the square of these residuals? One thing is by taking the sum of squares, having your prediction be above the line versus below the line. I mean, the actual value above the line versus the below the line. It's agnostic to that, right? And two, it happens that this has mathematics and leads to a nice thing. Okay, so we are lucky in that regard. Any questions? Least squared, curves fitting, sometimes you call it linear regression, okay, stuff like that. Now, what is that algorithm? This is, over here, the least squares curve fitting algorithm. And when you look at this, remember I said to you how I find linear algebra formulas opaque? Okay, this is an example of such a thing. Here we're saying we assume we have a collection of n points, each of which we have m variables on. We want to try find the parameters such that basically, actually, we want to find a a set of coefficients, okay, to multiply these data values to yield our target B. Okay, so maybe I've got this a little bit confused. We assume that our y values here are given by the vector B. Okay? The x values are given by the matrix A, right? This is a collection of rows. Each row corresponds to a point. Each column represents a variable on that, right? Actually, what I should do is replace the x by w. Okay, that's my mistake here. This is a w. Okay? What we want to do is to now multiply this by coefficients such that these are the coefficients such that w1 times x1 plus w2 times x2 plus w3 times x3 is equal to the appropriately b value. Okay? Any questions about my notation here? A is my matrix of data points. Okay?
Isn't a matrix, though, always going to be like a data point and a set of features?
Well, no. So what is a data matrix going to look like? I've got rows corresponding to each object. Yeah. I've got columns representing each feature. Right? This is n times m. Right. I want to make a prediction. I think this is the right way to do it, where for each one of these n things, take a minute, there is a target. If these are my training examples, if you wish, okay, I am going to want to be able to, for each one of these, there is some dependent variable, right? And what I would like to do is to find a set of coefficients. Okay, I think it's actually, what am I doing here? I think I'm going to multiply this by, I need something that is w by 1. That's n by, I need something that is m by 1. This is my w coefficient vector, right? And I want it so that the coefficients is at the x value times this plus the x, this is going to be a dot product, right? So it's this times this plus this times that plus this times that. My goal is to figure out these coefficients w such that I get that target value as closely as possible. Any questions about that? Okay? The claim is that this is how you do it. Okay? That you take your data matrix, you transpose it, multiply it by A, invert it, okay, multiply that by the transpose of A, and multiplies that by your target variable, and this will give you the coefficients matrix. Okay? Any questions about that? Yeah.
A W equal to B would have been done as W equal to A inverse B simply. This fancy way of writing like A transpose A inverse A transpose is equivalent to A transpose effectively.
No, well, first of all, this would be true. You say A times A transpose is a symmetric matrix, right? A symmetric matrix you can take the inverse of. What if you don't have a symmetric matrix? What if I don't have a matrix that is square? Okay, then you can't take the inverse of it. Okay? So this is one. So trying to grok this thing, this is a square matrix. M. Okay. A times A transpose. This is actually going to be, to be honest with you, this is going to be M times N times N times M. I got this wrong, right? That's bad. Okay. This will yield a square matrix. The transpose of this will yield the right dimension on that times P. Let's just see if we get this right. Okay, I'm not going to do this correct. If I had n items by m features, what is this going to do? It's going to give me one that is m by n, right? I multiply this by something that is n times m, right? And now, when I invert it, it's still going to be, this is an m by m product. Does everybody agree? This, I now multiply it by A transposed. What is A transposed? This was n by m. Now it's going to be m times n. Does everybody agree with that? And that makes sense. And what is B? Well, B is the target value on these things. This should be n by 1 because there's a value for each one. Okay? So someone send me mail to remind me, but this I'll have to change it. This basically, there's a reverse n and m and everything is fine. Any questions? Okay? Fair enough. So what does this mean? It means that solving least squares problems reduces to multiplying and inverting matrices. So if you have a good library that knows how to multiply matrices efficiently and invert them, this is a good, this is potentially a fast thing. Any questions? Okay. Now, where does this come from, or how do you think about it? Again, I don't want to go through the whole derivation. But in 2 dimensions, just to give you some intuition, if you're trying to fit one variable, so that your line is going to be an intercept plus a coefficient times your variable. When you work this thing out, the value of what the slope of that line is going to be works out to be this, xi, the sum over all points of xi minus x bar, yi minus x bar. What does this look like? Has anyone seen an equation like this anywhere along the line in the course? This is a, what you would call covariance thing on top. Covariance thing on top normalized by the variance, okay? Basically, this turns out to be the correlation of the 2 variables times the standard deviation of one variable divided by the standard deviation of the target. Any questions? So what does this mean if we want to interpret it? If we have a correlation of 0, what would we, between x and and y, what would we want the coefficient of x to be? Suppose we have an expression that looks like this, and we want to know this is IQ, and this is something that's completely independent of IQ, butter production in Bangladesh or something like that. What would we want that coefficient to be? 0. Does everybody see that? Uncorrelated means 0, right? Positively or negatively correlated means that, that it will have a positive relationship or a negative relationship, right? And if it's a correlation of 1, what do we want the coefficient to be? Suppose x is perfectly correlated to y. What do we want that correlation, that coefficient to be?
Plus 1 or minus 1?
It's not plus, it's not minus 1 because it's a positive correlation.
Okay, then
Do we want that coefficient to be 1? Let's say that we have something where my height, what's my height in feet versus my height in meters?
It should be greater than 1.
It's not greater than 1, not less than 1. Let's think about it. My height in feet, I am, let's say, 5.5 feet high. How many meters am I? 2 point something or other. What is the relationship between height and... Does everyone agree my correlation between someone's height in feet and height in meters should be 1, right? What is the correlate? What should be the multiplier here? It's a ratio between the ranges of the numbers. Does everybody kind of get that? And that's kind of what's happening here. The standard deviation is a function of how big the range of numbers is, right? So that's kind of showing you the way that normalization is, okay? Any questions? So the interesting property is that, that it's clear that the regression has something to do with correlation and normalizing things appropriately. To get the actual intercept, there's a nice property that the regression line has to pass through the mean of what the y values are and what the x values are. So here I've got one of the parameters. Once I know one of the parameters and I have a point on the line, I can figure out the other parameter. Okay? Any questions? Okay. So it should be clear now that there is a connection between, I think I need to move that again. There's a connection between, correlation and these coefficients. Okay, and that kind of makes sense. It should also see, if you look carefully at this, try to parse this expression. Notice that AT times A was what we used to compute the covariance relationship, right? The covariance matrix was exactly this kind of thing, okay? So you start seeing these things emerge. I'm not going to derive it, but you start seeing things that you would like to see happen emerging from this formula. Any questions? And if you ask really what it is, the reason why this is the right thing has to do with properties of orthogonal vectors and things. That if you think about it, what would be the error when we did a regression? What would be the error of the prediction? It would be the actual y value minus our prediction. Okay? If we did it for every one of these points, we would basically have a vector of errors that we made. We need that vector of errors to be such that if all the errors were on one side of the value of x, we could have reduced the errors by increasing the coefficient for that variable a little bit more. So there is a property that we need that the error vector has to be orthogonal to the vector associated with each variable. Vectors that are orthogonal to dot product to vectors means dot products of 0. And so you end up getting an equation that looks like this, okay? The 0 here kind of corresponds to the dot product being 0. And when you do this and you multiply it and you move the terms around, you get the equation that you want. Any questions about that? Okay? Bottom line is this gives us a way to compute what the optimal coefficients are as a function of matrix multiplication and inversion. Any questions? Well, okay, so what is the claim? The claim is, and again, I don't really want to do this, okay? What should be clear is you have to have the property that for any given, if we look at these predictions, every variable is contributing something to the predicted y value for every element, right? If we could reduce our error vector by changing one of the coefficients a little bit, that would mean that we didn't have the optimum one before. So we have the property that the errors can't be improved by tweaking the, the errors can't be improved by changing the coefficients, which works out to being that the error vectors are orthogonal to the values for each variable. Okay, this is the property you have to see that I'm not going to prove. If it's orthogonal, then the dot product of two orthogonal vectors is 0. and then you get this kind of thing. Okay? Any questions? Okay, but bottom line, we now have a way to solve for these coefficients. Any questions? Okay. So what I'd like to do now is to change gears a little bit and instead think, so now we have a way, if you believe that, of finding what is the optimal parameters for any data matrix. Okay, you have any data matrix, you have any target you want to predict, we can use that algorithm to find the linear regression for it, correct? Yeah.
Actually, I have a question from the last slide. So does that mean each time that we're doing the linear regression, we're always finding the optimal result because the errors cannot be fixed by adjusting the correlation that variable, right?
Well, we're finding the best fitting line through those points. A is the points, right? B is the target we're trying to fit.
Right. So when we solve that equation, we are like sure of the fact that this is the best fitting line that
We are sure that this is the line that minimizes the least square errors of this. Okay? And is that the best fitting line? If we define that as best fitting, then it is the best fitting. Okay? Any questions? Okay. So let's now look at how we can use these kind of linear regression, this curve fitting algorithm, to to build good regression models. And there's several different ways we can, you could just say, oh, here I've got a bunch of points, here I've got my target variables, run it through the machinery. There are several considerations that might come in. Okay? The first has to do with outliers. Okay? Here we have an example of a set of points where all of them lie on a line, but are pretty good except there's one outlier. Does everybody agree? The regression line, because there is a penalty that grows quadratically with how far you are from the thing, the regression line is very, very eager to make the outlier point happy. Does everybody see that? And so that one point pulls the line quite far away from where we want it to be. Okay? So, here the correlation was 0.4 with the with the outlier and 0.7 without it. Okay? So what is the lesson here? One possibility is that you should be careful, but when you're looking at your matrix, you should be looking for outliers before you solve your regression thing. Does everybody see that? How might we be able to, what might be another way, if we don't find the outliers before we solve the regression, what might we be able to do to...
Median instead of mean.
So, what...
You move one point at a time and see if it drastically improves.
So which point would you remove to make it, which point would you remove? Okay? The one with the highest residual, right? Okay? So again, you could conceivably fit everything, okay? Find out what is the point where there's the biggest difference between the right y value and our predicted y value, right? And keep iterating until it doesn't improve, okay? That would be one way to, or it doesn't improve by much, okay? But again, you may be throwing out real data, just, and you've got to decide if that's a good thing or not, okay?
So the system will change, right? Like if you just take the point with the highest residual error.
If I remove and then retrain. Once you remove that point of residual error, then you retrain the model. Okay, and now it will fit much better. So removing this one point gave us a much better fit to what's left. Okay, yeah.
I mean, you seem to allude to the idea that maybe it was just an error in observation, right?
Yeah.
But you wouldn't want to do this if you suspected it was an actual data point.
You wouldn't want to do it if there was an actual data point, right? So that's kind of the judgment call here, right? Throwing things away, produce a better fitting model. How can you produce the best fitting model? Use the statistician's rule. Throw out all but 2 points, right? And then you got a perfectly lying on a line. Okay? There's a vision of judgment here. Okay? It should be clear that that outliers are bad. Okay? If they are not good points. Okay? And if so, you should get rid of them. Okay? Any questions about that? The second issue that's important to think about when it comes to linear regression is the fact that often you don't want the right function isn't linear. Okay? So, you know, in a linear regression, we are going to take it, if you wish, it's going to be the sum, our equation is going to be the sum of the coefficient times x sub I. This is what we're saying that y is. Okay? But what if something has a nonlinear, if a variable has a nonlinear impact on the regression? Does everybody see we're estimating it wrong? What is an example of a variable that we think would have a nonlinear impact on a target? Can anybody come up with an example? A cubic or a square root. Yeah, but I mean, can anyone give an example of something? What? Height and BMI. Okay. So right. So if we think about it, the BMI was something like the mass over the height squared. Does everybody see that? Okay. So let's say we wanted to predict BMI. Right? Again, this might be the wrong thing to try to predict. But maybe we would be better off if we had something that was mass, was one of our variables, and we had height squared. Maybe we would do a better job if we had something that was a square term of it. Does everybody see that? It's not quite true from the example that we gave.
Do like any force with distance, like gravity.
What? Right. Suppose, let's say you wanted to figure out, if you're Isaac Newton, let's think that's an even better example. How did Isaac Newton discover the law of gravity? Okay. Wasn't this thing with the apple. What did he do? He sat there and he had this gravity machine that would measure the strength of gravity from something. And he had this thing and he saw that, that the gravitational force was a certain number of newtons when it was a distance of 1, and another amount when it was a distance 2, and another amount when it was distance 3. Okay? You could imagine Newton trying to figure this thing out. He didn't see a linear relationship between gravitational force and distance, right? Why was that? It was a quadratic thing. But if he had had the distance squared in his matrix, he might have done a better job fitting it. Okay? Any questions? That's not maybe yet convincing. But it should be clear that not all things grow linearly. Okay? Again, if we go back to the variables here, I think some of these things are probably better now. Is there any one of these things that we would think grows less linearly? I can probably believe that your weight does not grow linearly with the amount of food. But maybe it grows something like square root with the amount of food you eat, or something like that. That I can probably believe. Okay? Maybe it's the log of the food you eat, or something like that. Okay? So there's probably not really a linear relationship here. So how can we adapt our, our regression models, okay, so that we can deal with nonlinear terms, okay? Does anybody see what the problem I'm trying to solve here is? I'd like to be able to recover if the model in fact is that y is equal to food, the square root of food eaten times C1, I'd like to be able to figure that out, okay? What I can't, unfortunately, linear regression is going to give you something that's linear in its variables. But there's no law that says you can't add nonlinear terms to your variables. Okay? What does that mean? Suppose I wanted to try to build a model, and I had worlds where I had weight was my target. I had a weight vector. And for each person I had the amount of food that they ate. I could also compute a second row in a matrix that's going to be the square root of food. Does everybody see that? I could have food squared, add another value here, right? And now my feature matrix has 3 columns instead, not just f, but 3 columns, representing nonlinear functions of f, right? And now, if in fact the right relationship was that it's 2 square root f, if I do linear regression to try to predict what are the weight coefficients for this matrix, the coefficients I would get would be 0, 0, 2. Does everybody see that?
0,
Right, 0, 2, 0, excuse me, 0, 2, 0. Does everybody see that? So the technique here is I can add nonlinear values to what I'm doing, okay, if I'm willing to make my matrix larger, okay? How many people see what I'm doing here? How many people don't see what I'm doing here? Okay? Again, what is our goal? We are trying to come up with a model that is going to produce a linear combination of our features, right? Recognize that if you have a set of real features that you actually measured, once you have numbers in your data that correspond to real numbers, you could compute mathematical functions of your observations, right? By taking the square root of this number, 9, 25, I can compute 3, 5. Does everybody see that, again, it happens to be a place where everybody has food that's a perfect square, okay? But does everybody see what I'm doing here? If this is what you measured, I could produce a bigger feature matrix consisting of any transformation I want to any of your variables. I could square them, I could raise them to a power, I could do whatever I want with them. And now, trying to find the optimal coefficients for the sum of these variables, I have the ability to add the constant times the square root of f. I have a possibility to come up with what is essentially a nonlinear model, or a model that's a linear combination of nonlinear functions of my input. Any questions about that? Yeah.
Suppose y is a function of x to the power 1.234, something like that. So in that case, how many feature columns can we generate?
Okay, so what you're saying is this is great, okay? Here you're really saying this is f to the 0.5, right? Maybe we could also include f to the 0.51, f to the 0.52, f to the 0.53. Does everybody see that? We could make it a huge number of functions here, okay? And if one of these is right or some combination of these right, we'll get an even better fit. What is the problem? Okay? Obviously, you could use an unlimited number of these. I can guarantee you if you add enough columns as you have training examples, you'll come up with a perfect fit. But it's also a meaningless thing. Does everybody see that? Recognize that the good thing here is you can fit nonlinear terms. The bad thing is you have to specify what terms you need. And if you are too profligate, you end up with it being able to make a model from a lot of things that probably aren't right. Okay? And so there is some judgment here. Here you're explicitly deciding what nonlinear terms you're going to be adding as possibilities. Okay? If you add too many nonlinear possibilities, okay, nothing good's going to happen, right? If you add the wrong ones and not the right ones, nothing very good is going to happen, okay? But if you are judicious and you use the right, you think you know what the right powers are, you have the ability to fit a nonlinear model that does good things. Any questions about that?
Quite very difficult to analyze, like what all functions will be there in the given graph, square root, log, because
So you're saying, oh, it's very hard to figure that out. I mean, on one level, yes. On the other level, there's a small number of famous functions in the world. No one has ever cared about the function f to the 5.53, right? They cared about square root, they cared about log, they cared about cube, they cared about 1 over x, right? So I don't think that in general you are regretting that you can't include everything. There's a relatively small number of functions that tend to be interesting. And if you analyze what your problem is, you will probably know that, what the shape of it is. For the problem of trying to predict your weight from how much food you eat, do we think that the weight grows with the square of the food you eat? I don't think so, right? Do we think it grows sublinearly?
Yes.
So you do know something about what that right variable is, right? So you have some level of judgment about what you can add. Okay? Yeah.
So I guess I don't understand though how the adding the extra features helps with picking the correct one.
Well, it's not about, well, suppose, let's say, the right answer. In fact, suppose that it was the case that y was equal to 2 square root of f. Okay? And that was a perfect relationship, no errors, no something like that. If we have a bunch of values here, what would this mean? 2 squared, this would be 6. This would be 20. This would be, 16, I believe. This would be 10, I believe, right? And this would be 16. Now, if we have enough of these things so that we have well-determined functions. These are the y values, the targets, right? Does everybody see that if the target value really is, okay, a function of one of these nonlinear terms, the regression will have no trouble finding it, right? It's no harder in that case to find what the coefficient of the square root x term is than for the x term, okay? So if there is a nonlinear relationship and you have a hint as to what that might be, then including that column into what you're doing enables it to find it. Okay? Any questions?
But it will still be an approximation, right? Even if I know that it is sublinear, there are infinite functions which are sublinear. So
Well, okay, is it approximation? First of all, we're building a model.
yes.
Okay? A model is not the real thing. Okay? Sometimes it really is a square thing. That's what Isaac Newton found with this gravity, right? But usually we're trying to come up with a model. Okay? And it should be clear that certain models can be improved by having nonlinear terms. Okay? And it should be clear that if you have a hint where that is, you can add those terms and see if it does improve the model or not. Okay? Any questions about that? So this is a useful thing to do. Okay? Any questions? Okay. What is another useful thing to do? Okay? One useful thing to do is to make sure that you scale your features properly. Okay? And this is maybe less obvious and less, I've sort of talked about this, but what if we had a model we were trying to build, okay, where one of the variables was going to be something that's very large, like national population, and the other variable was something like reading literacy rate, which is a fraction between 0 and 1. If we try to build a model that's a linear model on these things, in order to make them come together, C1's got to be very, very small, and C2 has to be very, very large, right? And in principle, in the world of matrices being multiplied in perfectly precise arithmetic and stuff like that, it doesn't really matter. But in the real world of how these things get solved, there are numerical issues that tend to be a problem if the coefficients span big ranges. Okay? It should be clear if I divide this by by a million, there exists a coefficient that would work in these terms that are divided by a million, namely a million times bigger, right? So it doesn't really give you more power, but because of how these things get solved with numerical stability and numerical algorithms and things like this, it is often good to have your linear features all be about the same order of magnitude. Okay? And the best way to take a feature and reduce it to the same order of magnitude is to replace the values by z-scores. Does everybody get that idea? If I replace it by z-scores, now all of these values are going to be have a mean of 0, okay, and a standard deviation of 1. Does everybody see that? And now then, the coefficient should be roughly equal size, okay? And once we have them, we can go and reconvert them back to the original variable. Nothing's been changed. The z-score is just a linear transformation in itself. Okay? But it makes it easier for the computation. Any questions about that? Okay. The other thing to note is, and this is sort of a little bit like this thing, when you have power law distributed features, okay, you have to do something to it if you're trying to produce a normal target. Suppose, let's say, we're trying to produce, again, here's a model for how many years of education somebody's going to have as a function of how much education the parent has, how much income the parent has, right? If we leave income and multiply it by a constant, there is no way you can have a sensible value for in terms of years of education where income is a variable, no matter what that constant C is, right? You can't have more than 19 years or 100 years of education. If you would stay in grad school, you're literally your entire life, and you eat healthy, right? But it is clear that if you, for Bill Gates' income, you multiply that by any coefficient, if income is going to have any effect on small people, differences in income will have any effect on small people, it would immediately knock the value out of the scale for the higher order people. Does everybody see that? Now, why is the problem? The problem is not that the range of incomes is too big. The problem is that it is not normally distributed or linearly distributed. It is a power law distribution, okay? And so what you typically have to do is some kind of a transformation to a power law distributed variable. If you're trying to predict something that should have a normal distribution, and you're making it up from variables that are composed of things, those components should have a normal distribution too. Does everybody get that idea? If not, there's no way that you can use that variable sensibly. And so that's an argument that you need to normalize it. Z-scores won't normalize power law variables. How would you normalize a power law variable? You hit it with a log, right? You hit it with a sublinear function. And typically you hit it with a log or a square root. What's left then will be normally distributed. And thus wildly more useful to distribute to contribute to a model for a normally distributed thing. Does this make sense? Okay, good. The other property is, and this is basically saying the same thing the other way. If your target is power law distributed, and you're trying to, like predicting income, and you have how much they eat and how much, you have all these different variables, if the components of the variable are all normalized, the x values are all normal, and the y value is power law distributed, there is no way you could have the sum of a bunch of normally distributed variables is going to be normally distributed, right? So there's no way you can predict income from normally distributed variables. You might be able to predict the log of income from normally distributed variables, because the log of income is maybe normally distributed. And if so, that's the model you should be predicting. And then if you really want to figure out what their income is, once you have a prediction for the log of their income, you just jack it up to the right power to make a prediction for their income. Any questions? Any questions about any of these? Okay, because those are useful things to do with models. Okay? The other final, I guess, recommendation that I would have for building a regression model, a linear regression model, is to make sure you avoid highly correlated features. What happens if in your matrix we had, well, here, if you look at that, these are probably very highly correlated features. Does everybody kind of get that? Okay? So that's a danger here, right? Because f to the 4.51 is probably very close to f to the 0.52, right? Why is linear or having correlated, perfectly correlated or highly correlated features a problem? Suppose I had in my feature matrix my height in feet and my height in meters. These are perfectly correlated, right? It's the differences multiply it by 3.2 or something like that. Now, suppose that there is a case that my weight is equal to my height, a constant times my height is the right answer. What kind of a model could be built this way? Do you see that if I had both height and weight, height in meters and feet, it could be the case that y is equal to 10 times feet, or y is equal to, sort of 3.3 times the number of meters, right? Or equivalently, y could be equal to 5 times feet plus 1.65 times the number of meters. Does everybody see that if I had perfectly correlated variables, there would be many different functions that would give the exact same prediction? Does everybody see that? Which one of these is the right answer? All of them or any of them, right? But it's hard to interpret that, okay? If you looked at a function like this, you would be saying, wow, that seems like it only depends on 2 factors, right? Where in fact it really only depended upon 1 factor, right? But in addition to problems of interpretation, there are problems of numerical stability. Notice that, in our linear regression formula, we are going to be inverting a matrix, the covariance matrix. The covariance matrix is full rank only if there's not a linear dependence among the features in there, right? So if we did in fact have height and weight in our feature matrix, what would likely happen when we try to compute the optimal regression is it will come back with a numerical error. Does everybody see that? Okay? So this is kind of the problem. We need to find a way to deal with highly correlated features. And ideally, we should get them out of the matrix before we try to solve something like this. Any questions? How can we get away with these, eliminate these highly correlated features? So one possibility is to find the pairwise correlation between the features and say, hey, this is really high, then maybe I'll drop them or average them or something like that. Any other way we could do it? SVD, that's what we had at the beginning of this thing. You had this big complicated matrix thing. It would be great if SVD said, duh, this is really only this plus this, and then almost all the other things give you very little power, right? The good thing about SVD is it basically is going to eliminate highly correlated things. Okay, it will compress them into sort of essentially all the highly correlated variables into one. Okay, and then this problem doesn't exist anymore. Any questions about that?
And why would it not rank the top two when we are doing SVD?
Yeah.
We are trying to find out the row and column and the product, which would have which would help you make a better part of the picture.
The best approximation of the matrix, yeah.
So both of them, in height, if you're going back to this example, both in feet and meters, they will give you a good picture, right?
No. Let's go back to Lincoln here. What would happen is that if you wanted to predict, what it amounts to is if, recognize that, what are we doing here? Recognize, first of all, let's go back to what the math is to answer it. Here was our original rows and columns. We are losing the identity of what those column features are. After we've done this factorization, there is not a column that has the name height and feet anymore. There's not a column that says height and meters. Does everybody see that? But what should happen according to this is that if there were two very, very similar features, one of the columns and corresponding rows in this matrix, okay, is going to correspond to both of them. Does that kind of make sense? Okay, that's kind of the magic of it. And that the corresponding coefficient for that row/column is going to be very large. because that has a lot of predictive power. Okay? So that's kind of how this avoids the problem. Okay? Is that if those, it's creating a new set of dimensions. If we look back at Lincoln, here was the SVD of Lincoln. Does anybody see any Lincoln in here? You know, you don't see it, right? But you do see, if you look at it carefully, look at the stuff. Does anyone see a difference as we go from the most important singular singular vector to the least important? Does anybody see anything different as we move from left to right?
More noise.
Not more noise, I would say more detail. Okay, does that make sense? Okay? That what we want here is, the first one is a relatively simple matrix times a relatively simple matrix, right? The product of that is going to be a very blocky thing. Does everybody think of that? What should Lincoln look like? What would be the block?